Let's jump right into today's explainer, the ultimate foil boat challenge, the science of buoyancy. Okay, so picture this. You're holding a shiny, crinkly sheet of aluminum foil in one hand and a heavy, solid copper penny in the other. If you drop them, well, you know exactly what happens, right? But what if I told you we could completely defy those expectations using just a tiny bit of clever engineering? That is exactly what we're unpacking today. I mean, just think about the extreme contrast we're working with here. On one hand, we've got a heavy, solid metal penny. On the other, floppy, paper-thin aluminum foil. If you hold that foil up and blow on it, it literally flutters away in a gentle breeze. It's incredibly light, it's flimsy, and has a very low density. But the penny? Man, if you drop that heavy piece of metal into a tank of water, you get that instant heavy plop when it hits the surface, right? It goes straight to the bottom, it's dense, it's tough, and it sinks like a stone. Intuitively, our brains just tell us that heavy metal sinks and paper-thin stuff blows away. Okay, let's dive into this because we are about to completely flip that logic right on its head. The big question for this explainer is, can a seemingly flimsy foil boat actually hold 100 pennies without sinking? I know, it sounds totally impossible. Like, no way, right? How could a material that is literally paper-thin possibly support the massive, concentrated weight of all that solid metal? Well, to understand how we can engineer the impossible, we kind of have to look past our basic assumptions and dig into the actual physics at play. And that brings us to the core science here, buoyancy. Basically, buoyancy is just the science of how things float. But the really crucial thing to remember is that floating isn't just about weight. It's about water displacement and density. Take a massive cruise ship, for example. It's made of solid, heavy steel, weighing literally millions of pounds. By all standard logic, that thing should plummet to the ocean floor exactly like our penny. But it doesn't. It avoids that fate by displacing an amount of water equal to its massive weight. See, the shape of the hull traps air, which effectively lowers the overall density of the whole ship. If our little piece of foil is just perfectly flat, water's going to push right over it. But when we change its shape, we change the whole shebang. So when we fold up the edges of our foil, we actually trap a pocket of air. You basically have this invisible wrestling match taking place. The water is pushing up, but that trapped air creates this magic cushion of buoyancy that pushes right back. By shaping the foil into high walls, we're increasing the volume of our boat without significantly increasing its actual mass. This lowers the overall density of the structure, allowing it to displace a lot more water. And in this wrestling match, the upward buoyant force of the displaced water totally wins, holding our engineered boat safely right at the top of the surface. All right, so to see how this theory translates into some hands-on engineering, we need to gather our materials. Here's our Curiosity Labs supply checklist. Number 1, you're going to need some clean, standard aluminum foil. Try to grab a nice, square piece about the size of a paper book. Number 2, grab some safety scissors to trim those edges. Number 3, you'll want a ruler or a flat piece of cardboard. This is going to help you make perfectly crisp, straight structural folds. And finally, number 4, you're going to need your cargo, a giant mountain of pennies. Let's kick off the construction phase with design number 1. We like to call this the classic cargo pool. Step 1, lay your square of foil perfectly flat on the table, smooth as a calm lake. Step 2, fold all 4 edges straight up about 1 inch high. You're basically building the walls of a swimming pool here. And step 3, listen, this is the absolute most critical part of the entire build. You've got to pinch those 4 corners super, super tight. You need 0 leaks. A flat bottom, high walls, and tightly pinched corners are exactly what's going to keep the water out and protect your crucial air pocket from collapsing. But hey, engineering is all about testing different ideas, right? So what if we try an alternative approach? Enter design number 2, the speed canoe. You start with your flat sheet again, but this time you only fold up the 2 long sides to make long walls. Then roll and pinch the short ends really tightly into sharp, pointy tips. Just look at that aerodynamic shape. It looks like it could slice right down a rushing river, doesn't it? Super fast. But looking at the volume of trapped air can actually hold, I want you to guess right now. Which boat do you think will carry more heavy metal? Well, it's time for the climax of our explainer, the moment of truth. The engineering test. We're going to take our perfectly stable, high-walled classic cargo pool and place it gently onto the surface of our water tank. And there it is. It bobs slightly, perfectly balanced, just sitting right on top of the water like a majestic swan. The structure is sound. The displacement is active. Now the stakes are rising. It's time to load up our heavy treasure and push this foil to its absolute structural limits. Let's track the timeline on this stress test. At 10 seconds in, we've loaded 10 pennies. The boat has perfect balance. Honestly, it's practically begging for more weight. Fast forward to 30 seconds. We hit 30 pennies. Now the tension is definitely rising. You can see the waterline visibly creeping up the outside walls. The sheer mass is pushing the hull down, forcing it to displace way more water. And then 50 seconds. We drop in 50 pennies. Guys, we are officially in the danger zone now. The boat is dangerously low, it's wobbling, placement is literally everything right now. If you don't drop those pennies perfectly in the middle, the whole structure is going to instantly capsize. 58, 59, 60, 60 pennies! No way. That is a massive triumph of engineering. Just pause for a second and think about what is actually happening right here. A single, flimsy, crinkly piece of aluminum foil is successfully carrying the immense concentrated weight of 60 solid metal coins. It's just an incredible showcase of how manipulating a material's shape allows us to harness the physics of buoyancy and water displacement entirely to our advantage.
But of course, every engineered structure has an absolute limit, and our job is to find it. So, we add one more coin. 61 pennies. This is the tipping point. That single extra penny provides just enough downward force, increasing the density just enough to finally overcome our buoyant upward force. The water breaches those 1-inch walls. It rushes in, displacing the air, and down it goes. With a comical glug-glug, our glorious cargo pool sinks straight to the bottom of the tank.
And this brilliantly illustrates a fundamental mindset of literally any great researcher. When something sinks, that isn't a failure, that is valuable scientific data. Seriously, we don't get sad when the boat goes down. Finding the exact breaking point is the entire goal here. Sinking allows us to gather critical data on our structural limits so we know exactly what variables we need to tweak and how much volume we actually need to displace to make the next iteration of our boat even stronger. So, let's distill the core takeaways from our explainer today. First up, shape completely changes how materials behave. Flat foil sinks when pierced by weight, sure, but folding it allows it to hold massive loads just by lowering its overall density. Second, this whole thing works entirely because trapped air increases the volume of the boat, displacing enough water to create a powerful upward cushion of buoyancy that basically wrestles gravity to a standstill. And finally, number 3, never give up when an experiment sinks. We successfully manipulated floppy foil to do the seemingly impossible. And hey, a structural failure just means it's time to build a better model. Which leaves me with one final provocative question for you to ponder. How many pennies will your custom boat hold? Now that you understand the science of buoyancy and the relationship between hull walls, displacement, and trapped air, I'm challenging you to step up as the engineer. Build your own boat. Maybe try higher walls or a wider base. See if you can shatter that 60-penny high score. The materials are super simple, but the science is absolutely profound. So keep testing, keep tweaking those variables, and I will see you in the next explainer.